All right, class, welcome. Today, we're going to break down one of the most important electronic components ever invented. We're talking about the bipolar junction transistor, or as we'll call it, the BJT. Now, this little guy is the secret ingredient inside pretty much all the electronics you use every day. And by the end of this, you're going to understand exactly how it works. But first, let me ask you a question to get you thinking. How is it possible that something really small, something weak, can control something huge and powerful? I mean, think about it. How does your quiet voice get blasted across a massive stadium? Or how does one little tap on a button turn on a giant, power-hungry machine?
Well, it all boils down to one simple, powerful idea: control. In electronics, we call it amplification, using a tiny little signal to manage a much bigger flow of energy. And the undisputed master of this control is the transistor. That's the core idea we're going to unpack today.
Okay, so how do we actually build one of these things? Well, let's start with something you already know pretty well, the good old PN junction diode. We're going to see how a transistor is really just a clever upgrade to this basic component.
You'll remember that a diode is like a one-way street for electrical current, right? It's got a P-type side and an N-type side. Well, to make a BJT, we basically just take two diodes and smash them together to create a kind of semiconductor sandwich. It's a really simple but totally brilliant idea.
So let's look at the most common type, the NPN. On the left, you can see the actual structure. It's a super thin, lightly doped P-type layer, we call that the base, and it's squeezed between two N-type layers. One is the heavily doped emitter, and the other is the collector. And over on the right, that's how we draw it in our circuit diagrams. Now pay attention to that little arrow on the emitter. That's super important. It always points in the direction of conventional current flow.
And here's a cool little fact for you. The name transistor actually tells you exactly what it does. It's a mashup of the words transfer and resistor. Why? Because its whole job is to transfer a current from a low resistance part of a circuit to a high resistance part. That move right there is the secret sauce to amplification.
So, how in the world does this little NPN sandwich actually work its magic? The absolute best way to visualize this is to think of it like a very sensitive water valve. Let's run with that analogy for a bit. Okay, in any transistor circuit, you've got three currents to think about: the emitter current, the base current, and the collector current. So using our water valve analogy, that tiny little base current, IB, is like you using just your pinky finger to turn the knob on the valve. That one small action opens up the main pipe, allowing a massive gush of water, that's our collector current, IC, to flow through.
Now, here is the genius of the design and why it works so well. The base region is made to be incredibly thin, and it's not doped very much. What does that mean? It means when electrons shoot out from the emitter, only a very small number of them actually get used up in the base. The vast majority of them, like over 99%, just fly right across that thin base and get collected by the collector. It's this clever design that creates that huge collector current from a tiny base current.
You know, a transistor isn't a one-trick pony. It's more like a multi-tool. Depending on the voltages we apply to it, which is a process we call biasing, it can do three totally different jobs. And to really see these jobs, we need to look at its characteristic curve.
Okay guys, this graph is absolutely critical. I can almost guarantee you'll see this on an exam. What it shows is the relationship between the output collector current on the y-axis and the collector emitter voltage on the x-axis. And each of these curves represents a different, tiny input base current. You can clearly see three zones here: cutoff, active, and saturation. Each one tells us a different story.
So let's go back to our water valve. The cutoff region, where there's zero base current, that's the valve being completely shut. The transistor is off. Nothing flows. Then you have the saturation region. That's when we supply a large base current, which is like cranking the valve all the way open. Maximum current flows. The transistor is fully on.
But this middle part, the active region, that's where the real magic is. This is the sweet spot. Think of it like a dimmer switch or a volume knob. In this region, the big collector current is almost perfectly proportional to the tiny base current. So if we feed a small changing signal, like music, into the base, we get a big, perfectly copied, amplified version of that music out of the collector. That is amplification. All right, so now that we've got the theory down, let's connect these regions to what we actually use them for. And of course, let's talk about some really important stuff you'll need for your exams.
So to put it simply, when we want a transistor to act like a switch, which is the foundation of all digital computers, by the way, we're just flipping it back and forth between cutoff, which is off, and saturation, which is on.
But when we want to amplify something like an audio signal, we have to carefully set it up to operate right in the middle of that linear active region.
Okay, exam tip time. Get ready to write this down. The most important number for an amplifier is its current gain, and we call it beta. Beta tells you how good the transistor is at amplifying. It's simply the ratio of the big output current IC to the tiny input current IB. A typical beta can be anywhere from 20 to a few hundred. That means the output current can be hundreds of times bigger than the input.
This formula right here, beta equals IC divided by IB, is absolutely fundamental. You're going to use this in almost every single BJT calculation you do, so please burn this one into your memory.
Now, there is one other gain you should know about, and that's alpha. Alpha is the ratio of the collector current to the emitter current. And since we know the emitter current is just the collector and base currents added together, alpha is always going to be just a little bit less than 1, usually around 0.98 or 0.99. You'll see this one used in a different setup called the common base configuration.
And speaking of configurations, this table is exam gold. It compares the 3 different ways we can wire up a transistor. But look here. The common emitter, or CE, configuration is the superstar. Why? Because it gives us both high current gain, our friend beta, and high voltage gain. That's why it's the #1 choice for building amplifiers.
Whew, okay, that was a lot of information. So let's just pause and do a quick fire recap of the most important things you need to walk away with.
So, first, BJT is a 3-layer device. Second, it's a current-controlled valve. Small base current controls a big collector current. Third, it has 3 jobs: off, on, and amplifier. Fourth, the magic number for amplification is beta. And fifth, for most amplifiers we use the common emitter setup. If you've got those 5 points down, you are in great shape.
And just to give you a sense of scale, to really let this sink in, think about the processor chip inside your phone or your laptop. A single one of those chips can have over 100 billion of these tiny little transistor switches inside it. It's incredible.
So every computer, every phone, every single piece of modern tech that defines our world is built on this one elegant principle of control that we just talked about. This tiny switch is the Lego brick of our digital age. So the question I'll leave you with is, now that you know how the brick works, what are you going to build? Thanks for listening.